Hello, so today we're going to try something a little bit different. As you know, the UW canceled morning classes, but not the ones in the afternoon. So I'm going to see if I can record a lecture for you. And the students from both lectures are welcome to watch it online. So first let's revisit what we were doing last time. So going over to the slides here, all right, we were taking a look at velocity and acceleration. Right? And we learned that that's very simple to calculate if we have everything parameterized in terms of some time coordinate, because we can just take the derivative in each of the dimensions. So the y direction, we take a time derivative, and so on in the z direction, right? So the x, y, and z directions, we take a time derivative in each direction, and that's going to give us the velocity vector. We also learned a fact about when a curve can have constant length. Right, so you were asked to show that that this vector does not have constant length without actually computing its length, and that's due to a theorem we learned that said that if the position vector is perpendicular to the velocity, then the curve must have constant length. And what that looks like on the sphere, so here if I draw my position vector, so this green guy here, right, from the center of the sphere out to a point on the curve, on this red curve, right, and then if I go ahead and write in the velocity vector, so that's x prime, that these two have to be perpendicular because all the points on the sphere have position vector with length 1. Okay, and so these two are perpendicular on the sphere. And today we're also going to learn about the third direction. So if you can imagine a vector from this point and going in toward the center of the spiral, that's going to be a third direction that we have, and that's something related to the last slide on the last couple slides in the lecture about the binormal vector. Okay, so let's move along. Occasionally there are some things that I should have said in lecture and forgot. So one of them is I did not show this unusual parameterized curve to the second lecture, and I'll let you watch the video if you're interested. It's just an example of a very complex curve you can get out of a simple parameterization, right? So as these wheels spin around, you end up with this system of constraints that draws out a curve, but you have sort of a very complicated curve with a sort of simpler parameterization. You can go ahead and watch the video online if you're interested in knowing more. And then the other thing I wanted to revisit was this cycloid curve. So this is the curve you get if you take a point on the bicycle wheel and watch the curve that it traces as a function of time, right? And I noted that there were sort of singularities here when it came down to when it would touch the ground that looked like these cusps. Now, in fact, in the way we treat vector calculus, these are not as bad in our realm as they were in the type of calculus that you learned previously. And let's take a look at why that is. So our velocity vector, if you go over here, here's the formula for this, right? So our velocity vector, when we differentiate the position vector, is r minus cosine t, r minus r cosine t. And so that's the change in the x direction, and r sine t is the change in the y direction. And if I calculate v of 0, you notice that I get r minus r, right? So that's 0. And here I get r times 0, right? So in fact, my velocity has length 0. In other words, that the rate of change shrinks to 0 as I come down into this point. So the actual velocity vector is a continuous object. But what we don't have in this case is let's see. I want that on the bottom. What we don't have in this case, right, is a normalized version of the velocity vector. In other words, I cannot divide by 0 here and get a direction. And so the direction changes pretty abruptly from, a vector that as you come down in this curve, the velocity might be pointing in this direction. When I come back up out of the curve, it's pointing in this direction, and there's no way as a unit vector for me to flip this around in a continuous way. And then finally, if you check check the values of the acceleration vector, you'll see that when I come down to the bottom of the curve here, my acceleration points straight up, right? So it wants to come down, and then there's a force that pushes this point back up. And then at the top of the curve, the acceleration is going to point straight down. So there's a force that wants to pull that point back down on the curve, and so this just repeats. All right, so moving along, what we would like to do today is study arc length. So if I draw some curve here, right, I would like to know the total length of this curve. So say I have it parameterized from t equals 0 to t equals 1, and I'm going to go back to a formula that you may have learned already. If you haven't, it's easy to understand in the context of everything else I'll describe today. But suppose I had, right, some time point here, t equals 1, and here, right, so here's t equals 0, and here's t equals 1. And the formula we learned for the arc length, so if this graph looks like y equals f of t, the formula we learned for the total arc length was the integral from 0 to 1 of 1 plus y prime of t squared dt. Okay, so you may have just memorized that formula and didn't know where it came from, which is fine. But today we're going to learn a generalization of this fact that will allow us to calculate any type of curve, including curves in three-dimensional space, or curves that don't look like the graph of a function like this one does. Okay, so how do we do that? Again, I'm going to draw my curve, right? And I'm going to pick 2 points on my curve here. So let's suppose this is a point, x of t, and this is a second point, and we'll say that's x of t plus delta t, right? And then there are, say if I pick my origin here, right, there are these position vectors, x of t and x of t plus delta t. Don't worry about these too much, except they appear in the formulas. And so what we would like to do is estimate a distance, right? A distance for this part of the curve using the distance between these 2 points, which is also the same as the distance if we subtract these vectors, right, and then take a length. Okay, so what is that? If I calculate this, right, if I calculate this directly, so I have x of t plus delta t minus x of t, right? And then I have this distance. In other words, the length of this straight line, so I'll call this delta s, right? So delta s is going to be the contribution to the total arc length that comes from this small segment, okay? So delta s, right, is actually equal to this quantity here. Okay? So then delta s is this guy. And what we would like to do is come up with some nice formula for delta s. Right? So notice that if I can rewrite this as x of t plus delta t minus x of t, and now I'm going to multiply and divide. So I'm going to divide by a delta t, and then I'm going to multiply by another delta t. So let me just make a little more room here. And I get this formula. Now this part of the formula, the second part of the formula here, we've seen before, right? So this is approximately x prime of t. So this is the length here of x prime of t, right, times delta t. In other words, that the change in arc length can be represented as the length of the velocity vector times the unit of time that it took to go from this point to this point. And notice in terms of arc length, it doesn't matter how fast we parameterize this curve. So if I go from here to here, say in some particular time point, I can also go between the two time points twice as fast. Okay, so if I go twice as fast, x prime of t, that vector is magnified by a factor of 2. In other words, this term gets doubled if I go twice as fast. But I get there in half of the amount of time, right? So then delta t is shrunk by a factor of 2. Right, so if I go faster, right, I expand this part and I shrink this part by the same amount. Okay, so all of the math works out independently of how quickly we parameterize the curve. Now we're gonna expand on this formula here, right, and we're gonna set up some integral equations that show us how to actually calculate this. Let me leave that part up. And then I will write, okay, so I have delta s is approximately, right, x prime of t dt. So if I want to calculate the total arc length, you can see that I have something that looks like, so let's suppose I'm going from time point 0 to time point 1, okay. I'm going from t equals 0 to t equals 1, okay, and I want to integrate, right, delta, I want to integrate, say, ds dt. Okay. Okay. So that integral is in the correct form. Now notice if I take, right, if I divide both sides of this equation by delta t, I get delta t, right, delta s over delta t is approximately this guy. The continuous version of delta s over delta t is ds dt, which is what happens if I shrink all of the limit, right? If I shrink the time point down, or the time interval down to 0, right? And what I get is this formula, right? So instead of instead of using kind of the approximation here, I have the continuous version, and you can see that arc length. Let me put vectors here. Right? If I take the norm of the velocity vector and integrate it as a function of time, that what I get is this formula. And if I revisit my curve, right, the curve that I just looked at, where I had where I parameterize it, say, as x of t equals t, y of t is equal to some function of t. Okay, when I plug it into this formula, I get so this is the vector x of t here. What I get for the length of the vector, when I differentiate the x coordinate, I get 1. And when I differentiate the y coordinate with respect to t, I get f prime of t. So I square that. And that's actually this 1 plus f prime squared that you've seen in your integrals is a special case of this more generalized formula. Okay, so in the generalized case, right, we may have any function here, right, any function for the x coordinate, any function for the y coordinate, and if we have a z coordinate, we can have a function, any function there. So the general case, right, so in the general case, where I have x of t, y of t, and I'll go ahead and put a z of t here too. What does this look like? My x prime vector looks like, right, so my scalar x prime of t, scalar y prime of t, scalar z prime of t, and I get this formula, x prime of t squared plus y prime of t squared, oops, plus z prime of t squared dt. All right, so my length, the length of the velocity works out to be this formula, where I just take the length of the velocity vector. So you can pause the video at any time, and if you have any resolution issues while the video is playing with the PDF, if you pause it, it tends to resolve itself. So if you're having any bandwidth issues or something, you can go ahead and pause and take a look at the formulas or back up. But in any case, we basically derived now this formula, right? So this was our special case here, where S was this integral from some a to b of 1 plus y prime squared, so the square root of that. And then we've now generalized, right? We've now generalized the formula. And we're going to, from there we're going to move on to something called the arc length derivative, which is something a little more complicated than the time derivative, but easy to understand. So one way to understand the difference between a time derivative and an arc length derivative is to think about you're driving through the mountains. Okay, and so I'm driving up the mountain and down the mountain and up the mountain and down the mountain and so on. And say my function, the function I'm graphing here is altitude, and here we have time. Okay. Now notice that if I take a segment, right? If I take a segment here and I want to know how much my altitude changed, there are a couple different ways I can measure that, right? So I can measure the change in altitude as a function of time. So altitude as a function of time depends on how fast you're driving. Right? So if this curve here is my x of t curve, right? So altitude as a function of time depends on, right, the magnitude of my velocity. Now, on the other hand, you could ask, how much did my altitude change if I go 40 feet, right, 40 feet ahead? And that doesn't matter whether you covered that 40 feet in 1 second or 20 seconds, right? The altitude change is the same. So we have another way of looking at altitude, right, as a function of distance traveled. Okay, so altitude as a function of distance traveled is related to something a more general notion that we would call the arc length derivative. So we're looking at the change, in some function, right? In this case, altitude. So altitude is sort of our f of t. And we'd like to, right, so we'd like to know how that changes as a function of time and how it changes as a function of distance. And those are two different but related things. And so we'll learn the formula that's going to help us relate them. All right, so we want the change in f divided by, right, the change in position. So I'm going to put, so this is our point, right? So this is our position x. So how much, right? So how much distance did we cover is, right, essentially a question of if I have this point x of t and this point x of t plus delta t, right, what is this distance here? So that's what goes in the denominator here. So this is, say, x of t plus delta t minus x of t, and we can take the distance. And this is the same whether we sort of calculate the distance between the points, or in the formulas, it's the norm of the velocity vector, so the length of the velocity vector. Right, so that's what we get on the bottom here. On the top, you see that we just get f of t plus delta t minus f of t, right? So this is the formula, right? So this is the change in f, right, as a function of distance. Now, expanding on that from this formula here, let's go ahead and rewrite this into two pieces. Right, so delta f over delta x, or sorry, I'm going to write the first term to look like a time derivative. Right, so this is going to be f of t plus delta t minus f of t over delta t. So that's going to be our first term. Now I'm going to multiply it by a second term. Right, so I've now divided by delta t. I need to multiply by it again. So I'm going to multiply by this quantity, which is delta t over, right, and if I reduce this term here, well, let me just leave it discretized. Here I have delta t, right, over the length delta x, right, where this is the position vector. So this is a length in three-dimensional space. And again, I'll go ahead and write this as a vector. So now I have two terms, right, this term and this term. The first term is f prime of t. The second term is a little harder to understand, but imagine having it flipped over. Okay, so imagine, let's just do a little side calculation here. If I flip it over, oops, I need a delta in there. Okay, I basically flipped this guy over. Okay, what is this top guy is the change in position, right? The amount that we've traveled in distance between these 2 points. So that is this quantity. And this is a delta t, right? So this is the same thing as our delta s, right? And so here, right, we have this delta s, actually I should say delta s over delta t, right? So this change here on the top is the change in arc length, right? So the distance that we've added from going from this point to this point. So that's delta s, right? So we have this formula where this change in position, delta s divided by delta t, right, is is approximately, or is equal to this, and if we, or the reciprocal of that, and then if we like, we can replace it with the continuous version, which is, so the continuous version of delta s over delta t is ds dt, and I screwed this up slightly. What I want here is not ds dt, but dt ds. In other words, right, so we had flipped it over from here to here, and now we're going to flip this back, right? Okay, and so we've learned how, right, the arc length changes as a function of time, right? What is this guy, right? What is that guy? So let's go over here, right? So we have here our function. So what I'm highlighting here in green, on the slide is the term that corresponds to this f prime of t, right? And what is left over, let me change the color here. What is left over is this pink term, which is the reciprocal of velocity. So, right, ds dt is equal to the magnitude of velocity. In other words, that the distance, right, the total distance that we travel is measured, right, by this change in velocity, or the magnitude of this velocity. Okay, so all in all, then we get this arc length derivative formula, okay, and it says that the change, right, that the change in some function in terms of arc length, we can divide it up and say that this is df dt times dt ds. Okay, so df dt is the same thing as f prime of t, and dt ds is equal to 1 over the magnitude of velocity, and this is because ds dt, right, is equal to this. And so from that we get a formula that allows us to calculate the total arc length. Right, so let's go ahead and erase this guy. Oh, sorry. That calculates the arc length derivative, which is df df. So this is the arc length derivative. Right, which is the product of this time derivative in a correction term. And the correction term basically accounts for the fact that I can cover, right, the distance fast or slow, right? And so this scaling term just basically corrects for the fact that if I take the curve twice as fast, right, then this term gets doubled, this term gets cut in half, right? So that the derivative with respect to the arc length is the same. Okay, so it all should work out. All right, so what are some real-world applications of this kind of mathematics? I was talking to some friends who work for a company called Oculus in Southern California, and they are developing virtual reality gaming software. And so some of you may have heard of the Oculus Rift. Seems to be the new darling of the tech world. And by the way, they are hiring 100 people in the very near future. So there are jobs available in this kind of in this technology sector. But in any case, what they have are these virtual reality goggles that you put on and you move your head, right? And what should happen in the virtual world is as you move your head, right, the virtual world moves in sync with how you're moving your head in physical space. And what happens if you don't calculate this correctly? There are various videos posted online of people getting quite sick actually from having a disconnect when they turn their head and the virtual world doesn't turn quickly enough. So they have these gyroscopes that are sitting inside the virtual reality goggles that make measurements as to the velocity that you're turning and so on. And you have to piece this together using an integral and figure out how much somebody actually turned their head. And again, if you get this wrong, then people can get quite sick, and so they even have this little game they were testing out called Don't Vomit. Anyway, but that's sort of a fun, fun real-world application of this, of some of these ideas. So let's move on to curvature. Okay, so let's move on to curvature. So we've learned about, right? So we've learned about position. Right, so we've learned about position, and then this is maybe my position vector. And we've learned about velocity and tangent, right? So from this curve we have some tangent that should be, right, the tangent direction should go in the same direction as the velocity, okay? And so we can define something called a unit tangent vector. So provided that the length of v is not 0, we can pick a unit tangent vector in the same direction. And it's just I keep putting the distance on the top. Okay. So the vector t is the vector x and normalized by its length, right? So the length of the vector t is always going to be 1, and its direction goes in the direction of the velocity. And so here, over on the slides, you can see the formula for t, right? And in fact, this is the same normalization. If you remember, when we divided by the length of velocity, this was our conversion between arc length. This gave us a conversion factor between arc length, right, and the time parameterization. So in fact, this formula v over the norm of v right, so this guy is the same as x prime. And if I expand that out, this term here becomes dx dt. Let's be correct and put our little vectors here. And we remember that this this reciprocal of velocity, so the dividing by the length of x prime, was the same as dt ds, right? So in fact, our tangent, right, our unit tangent vector here works out to be the arc length derivative of the position vector when we combine these two terms. Okay, so so you can see the formula here that we have our arc length derivative just by normalizing. And in fact, taking an arc length derivative, there'll be a general formula where you take the derivative and then you divide by the length, right? So to take the arc length derivative, you calculate the velocity and then you divide by the length of the velocity, the magnitude of the velocity, right? And that's arc length derivative. So to get, just to work out a couple of simple examples. Right, to work out a couple of simple examples, let's suppose that our curve here, let's see what I've used for notation. So x of t is going to be some fixed vector b plus t times some fixed vector c, right? And we learned that this actually will trace out a line, right? So you have some initial vector here b, right, going from your origin. And then to that you would like to add, right, you would like to start adding, so if c goes in this direction, I'm going to keep moving in the direction of c, right, and I'm going to trace out my position curve will go along this purple here. Okay. Now if I take x prime of t, if I calculate that, right, so this term drops out when I take a derivative because this is a constant vector. So when I take a time derivative, it's just 0. Okay? And when I take a time derivative of this guy, I simply get c. And so our unit tangent, in this case, assuming c is not 0, right, my unit tangent will be c divided by its length. Right, so this is not a difficult calculation once you understand how to do it. But all the cases will basically be the same. Take the time derivative, right, and then divide by its length, and I have the arc length derivative. So now the next thing we're going to do after you've done a couple in-class questions is we're going to apply the operation of differentiating by time and normalizing by the velocity. We're going to apply that twice, and we're going to get something that tells us how much the curve is curved. Right? So this is a straight line. The curve is not curved at all. And so we should expect that calculation to give us 0 in that case. So let's find out in a minute. First, I'd like you to do a couple problems yourself. So going over here to the in-class questions, right? Calculate. I've given you a vector function. So this is just your circle. And then what I'm asking you to do is the calculation where you're calculating arc length of the circle from 0 to pi over 2. So a picture of that looks like, right, here's my circle, and I'm parameterizing it, right, from t equals 0 to t equals pi over 2. And I'm asking you to calculate, draw it in purple, I'm asking you to calculate this arc length. Right? You should know how to calculate the answer because you know the total length around the curve. Right? But go ahead and do it as an integral formula. And then there are two related cases. One of them is the function where I have 3 e to the t, 4 e to the t, right? And I want you to think about what that curve looks like, and then calculate its arc length from 0, oops, oh, I can't get it to select what I want. Calculate the arc length from 0 to log 2. This just makes the math work out nice and easy. And I'd like you to compare that with what happens if you take the arc length of the function. So the next function is x of t is equal to 3t, 4t, okay? And calculate its length between time points 1 and 0. So I'm going to give you a couple minutes to do that, and then we're going to come back and we'll go through the answers.